Everyone talks about Newton and the apple, the falling fruit, the legend. But nobody talks about what happened in the 24 hours before he actually understood motion. Not gravity falling down. Motion itself. The rules that govern every single thing that moves in this universe. August 1684 in Cambridge. Newton is 41 years old. He has not published anything major in over a decade. Most people in London think he is done. A recluse obsessed with alchemy and theology. Then Edmund Halley walks into his rooms at Trinity College with a question that will change everything. He claims he calculated this years ago but cannot find the proof. He promises to send it. 3 months pass. November 1684 arrives. Newton has not sent anything, but something has changed inside his mind. For 18 years since 1666, when plague shut Cambridge and sent him home to Woolsthorpe Manor, he has been sitting on pieces of a puzzle. The mathematics of curves, the behavior of light through prisms, the idea that the same force pulling an apple might extend to the moon, but he never connected them. He never saw the complete picture, not until now. The tract that contained 10 propositions, 3 theorems, 7 problems. The foundation of everything we now call physics. This is not about genius striking like lightning. This is about a man who kept a problem constantly before his mind until the first dawnings opened slowly into full and clear light. His own words. This is about the specific moment when scattered fragments became a system. If you value documented history like this, subscribe. It is the best way to support our work. Also comment from which city you are hearing this from. This script is researched and factual, using sources from the Stanford Encyclopedia of Philosophy's comprehensive Newton entry, last updated December 2024, and from Cambridge University Library's Newton Papers collection, particularly manuscript Ad 3965 containing Newton's handwritten draft of De Motu. These are not general overviews. These are primary documents, original manuscripts, dated correspondence, the actual papers Newton touched. Now back to the information. Forgets to sleep? When he walks in his garden, he rushes back with new thoughts and begins writing before sitting down. His chemical notebooks, which normally contain dated entries for every experiment, show no entries from May 1684 to April 1686. Nothing. For nearly 2 years, Newton abandons pursuits to which he was formerly dedicated. Alchemy, theology, everything stops. Only this problem exists. Here's what sits in front of him that day. Halley's question about planetary motion. But underneath that question lies a deeper one that Newton has been circling since 1679, 5 years earlier, November 1679. Robert Hooke writes to Newton. Hooke is curator of correspondence for the Royal Society. He is trying to rekindle their relationship after years of hostility over optics. Hooke sends a letter proposing a new way to think about planetary orbits, compounding the celestial motions of the planets of a direct motion by the tangent and an attractive motion towards the central body. Newton later claims he never heard this idea before. Historians call this claim disingenuous, maybe a lie, but whether Newton learned it from Hooke or discovered it independently does not matter for what happens next. Before Hooke's letter in 1679, Newton thinks of orbits as equilibrium, a balance between an endeavor to recede from the center during circular motion and some attractive force pulling inward. After Hooke's letter, whether he admits it or not, Newton shifts to a different conception. The orbit is not equilibrium. The orbit is continuous freefall, a body moving in a straight line that is constantly deflected by a central force. Hooke cannot prove this mathematically. He has intuition, analogies, experiments with swinging balls and cones, but no equations, no rigorous demonstrations, just the hint of something true. Newton works on this privately in early 1680. He derives that the path is an ellipse. He proves Kepler's second law, equal areas in equal times, conservation of angular momentum expressed geometrically. He does not publish. He does not tell anyone. He puts the paper somewhere in the chaos of his rooms and moves on to other work. Alchemy, biblical chronology, the nature of prophecy. The orbit problem sits dormant. Fast forward to August 1684. Halley arrives. Newton claims he solved this years ago but cannot find the proof. This is not entirely a lie. He did work on it, but the work was incomplete. The breakthrough has not happened yet. What Newton worked out in 1680 was the special case. Circular orbits, maybe elliptical orbits for one specific force law. He has not yet understood the general principle. He has not yet formulated the laws of motion themselves. De Motu will not contain the law of universal gravitation. Even more remarkable, De Motu will not contain the 3 laws of motion. Not yet. Those come later during the revision process. What Newton promises Halley is not the full Principia. It is a starting point. But even to write that starting point, Newton needs something he does not have in August. He needs to see the complete structure. These are empirical observations. Kepler knew the orbits were elliptical and guessed at the mathematics. Newton's task is to show why, to derive these laws from deeper principles. Combine this with Kepler's third law, and the force must be inverse square. Simple, but circles are not ellipses. The planets do not move in circles. Kepler discovered this 70 years ago. The real orbits are elliptical, variable distance, variable speed. How does Newton go from the simple case to the general case? What we now call calculus. He developed this in 1666 at Woolsthorpe during the plague years, his theory of fluxions, a geometric method for dealing with infinitesimal changes, finding slopes of curves, finding areas under curves. By October 1666, he wrote a manuscript summarizing everything he learned, extending the work of Descartes, Viet, Wallis. He never published it. Only a few people in London knew about it through private circulation, but Newton has this tool available, the method of first and last ratios. Limits expressed geometrically, but he has not yet stated the principles that tie everything together, the axioms, the foundations. This is what suddenly becomes clear, not in a flash, not in a single moment, but in a slow accumulation over hours or days, when Newton is so absorbed he forgets food and sleep and the state of his clothes, when the problem has been kept constantly before his mind for so long that the solution finally reveals itself. Motion is change. A body in motion stays in motion unless acted upon. First law, inertia. Galileo glimpsed it. Newton makes it precise. Force equals the change of motion. The change of velocity times mass. Second law. The force law, quantitative. Once Newton has these principles, everything follows. Orbital motion becomes a mathematical problem. Body moving. Force pulling toward center. Using his geometric calculus, Newton divides the orbit into infinitesimal triangles. Shows that if force is directed toward a center, the body sweeps equal areas in equal times. Kepler's second law derived from deeper principles. He calculates what force law produces an ellipse. Answer: inverse square. Kepler's first law derived mathematically. Then the inverse problem. Given inverse square force, what is the path? A conic section. Circle, ellipse, parabola, or hyperbola depending on initial conditions. For planets, ellipses. For comets, parabolas or hyperbolas. This is power. Predict trajectories for objects never seen. Newton coins this term. Before this manuscript, the concept does not exist with this name. Inherent force, the idea that prepares for inertia. Resistance, the property of a medium that impedes motion. These definitions set up the framework. Then 4 hypotheses. Later editions of Principia will reframe these as rules and phenomena. But in de motu, they are starting assumptions. Bodies move in orbits. The force is directed toward the center. The force varies with distance. These are not proven. They are assumed based on observation. Perpendicular to the radius is conserved. This reappears as Proposition 1, Theorem 1 of Principia. Theorem 2, for circular motion, the centripetal force is proportional to the square of the arc length and inversely proportional to the radius. This gives the quantitative measure of force for uniform circular motion. Theorem 3, for Keplerian elliptical motion, the force is inverse square. This is the key result. The mathematical demonstration that an ellipse with the sun at one focus requires an inverse square central force. Problem 5 discusses resistance. Problem 6 and 7 deal with motion in resisting media. Newton extending theory beyond pure orbital mechanics. Projectiles in atmosphere. Bodies falling through fluids. Motion under combined forces. The manuscript Newton sends to Halley is dated November 1684. Arrives in London early December. Halley presents it to the Royal Society, December 10th, 1684. He is ecstatic. Mathematical originality. Physical implications. This is not just solving planetary orbits. This is a new way of doing natural philosophy. Halley immediately returns to Cambridge in November, right after receiving the tract. He asks for more. He sees this small manuscript can become something greater. Newton agrees. He begins expanding. The 9-page tract becomes 500 pages, 192 propositions, 3 books instead of 2. Book 1 to London Spring, 1686. Books 2 and 3, March and April 1687. Complete Principia comes off. Press, summer 1687, roughly 300 copies. Samuel Pepys signs imprimatur, July 5th, 1686. Published, July 5th, 1687. This date marks the beginning of modern physics. Newton has worked on gravity and orbits since the 1660s. Calculated moon's centripetal acceleration matches inverse square from Earth. Satisfied himself, Earth's gravity holds the moon. But he did not have the framework to generalize, did not have laws of motion stated as axioms, did not see how to derive complex phenomena from simple principles. Halley's visit and 3 months' concentrated work breaks the barrier. Here is what Newton later says. In a letter to Halley, June 1686, he writes about his right to the ellipse. Even if Hooke suggested inverse square law, Newton derived the mathematics. Kepler knew orbit was oval and guessed elliptical. Hooke, without knowing what Newton found, can know only that proportion was inverse square approximately at great distances. Only Newton proved it rigorously. Only Newton showed what force law produces ellipse and what orbit inverse square force produces. This distinction matters. Hooke has intuition, Newton has demonstration. Once he writes definitions and laws at beginning of de motu, everything follows by mathematical necessity. This separates Newton from everyone before. Galileo studied falling bodies. Kepler discovered empirical laws. Huygens analyzed centrifugal force. Hooke speculated about orbits. But Newton synthesizes everything into unified mathematical theory with stated axioms and derived theorems. He invents mathematical physics as a discipline. Before Newton, natural philosophy proceeds by observation and speculation. After Newton, physics proceeds by mathematical derivation from stated principles. The breakthrough is seeing how they fit. Start with definitions, state laws of motion, prove theorems about force and trajectories, solve problems of increasing complexity. The structure of de motu and later Principia reflects logical order in which truth must be established. Newton begins with what can be defined: centripetal force directed toward center, fundamental concept for orbital motion. He distinguishes it from centrifugal force, Huygens' term for apparent outward force. Newton inverts perspective. Real force is centripetal, inward. This conceptual shift is crucial, connects to second definition, inherent force, vis incita. Inertia, body at rest stays at rest. Body in motion continues unless acted upon. This becomes first law in Principia. Third definition is resistance, property of media opposing motion. Newton includes it because he is thinking beyond celestial mechanics. Wants theory handling motion and resisting media. Each one proved. First theorem proves any centripetal force produces equal area in equal time. Kepler's second law, generalized, applies to any body under central force. Proof is geometric. Divide orbit into infinitesimal segments. Second theorem quantifies force for circular motion. No radius and speed. Calculate centripetal force. Newton worked this out 1666. Now presents it systematically. Third theorem is culmination. For Keplerian elliptical motion with center at one focus, force is inverse square. Proof combines geometry and calculus. This is mathematical demonstration Hooke could not provide. Too much velocity and the body escapes on a hyperbolic path. Just the right velocity produces a circular or elliptical orbit. This explains comets. They are not distinct from planets. They obey the same force law. They simply have different orbital parameters. Some comets have elliptical orbits and return periodically. Others have parabolic or hyperbolic paths and pass through the solar system once. Newton finishes the tract with problems on resistance. What happens when a body moves through a medium that opposes motion? He considers two cases: motion in a straight line with resistance proportional to velocity, motion toward a center with both inverse square attraction and linear resistance. These problems use hyperbolic constructions to solve what are effectively differential equations. Newton's geometric method is his version of calculus. He avoids the symbolic notation that Leibniz will later develop. Instead, Newton works with curves and limits, areas and ratios. This makes his proofs difficult to follow for modern readers. But it is rigorous. Each step is geometrically justified. Each conclusion follows from premises. Newton points out that the horizontal and vertical components can be separated. Horizontal motion is affected by air resistance. Vertical motion is affected by both resistance and gravity. This shows Newton thinking like a physicist, decomposing complex motion into components, treating each component with the appropriate force, then combining the results. This method becomes standard in physics, but in 1684 it is novel. Most natural philosophers still think in terms of total motion. Newton sees that vector components are the key to analyzing real-world problems, but does not state foundations clearly. Laws of motion not explicitly formulated, law of universal gravitation not stated. Gaps get filled over next 2 years. De motu does not contain first law explicitly. Idea is there in definition of inherent force, but Newton has not stated it as axiom. Only when revising does he embrace principle of inertia as first law. Similarly, second law, not yet stated. Newton calculates forces for specific cases, but has not formulated general principle. Force equals change of motion. This comes during revision. Third law also does not appear. Action and reaction. Every action has equal opposite reaction. Crucial for understanding interactions. When Earth pulls Moon, Moon pulls Earth. Newton includes this in Principia, but not original tract. Most importantly, de motu does not state law of universal gravitation. It proves planetary orbits require inverse square forces, but does not say every particle attracts every other particle with force proportional to product of masses and inversely proportional to square of distance. This universal law comes later, grand synthesis. Expands 10 proposition tract into 500-page Principia. Tract becomes Book 1. Newton adds Book 2 on motion and resisting media. Book 3 applying theory to solar system, calculating masses and distances, explaining tides, predicting cometary orbits. Final version has 192 derived propositions, each proved rigorously. Structure like Euclid's elements, definitions, axioms, propositions, corollaries, scholia. Newton's model, not speculative philosophy, not just experimental philosophy, combines mathematical rigor with empirical grounding, states principles, derives consequences, tests predictions. When theory matches phenomena, theory is confirmed. When discrepancies appear, theory is refined. Mechanical universe obeys mathematical laws. Laws discovered through reason and experiment, once discovered, allow precise predictions, motion of planets, paths of comets, tides, pendulums. Everything follows same principles. The Principia provides framework for classical mechanics, remains foundation until Einstein's relativity, early 20th century. Even then, Newton's laws are not wrong. They are approximations valid for everyday speeds and distances. Not a single brilliant thought, a patient synthesis of 18 years of scattered work, mathematics developed during the plague years, physical insights from studying at Galileo, Descartes, Huygens, the stimulus of Hooke's correspondence, the question from Halley. All of these converge. Newton keeps the problem constantly before his mind. He forgets to eat, forgets to sleep, abandons alchemy and theology. Works for nearly 2 years on this single project. The result changes human understanding of the universe. This is not clean copy, this is working manuscript. Newton developing ideas as he writes, proving one proposition, seeing it leads to the next, building the logical structure step by step. Halley received this draft and had it registered with the Royal Society on December 10th, 1684. The Royal Society's copy exists in their archives. Multiple versions of de motu survive, showing Newton's revisions, even of the short tract. He rewrites, clarifies, expands. Each version is better structured, more complete. By the time the tract becomes Principia, it is transformed. He returns to Cambridge and urges Newton to expand it. Newton agrees. By spring 1686, the manuscript of Book 1 is ready. Newton presents it to the Royal Society on April 28, 1686. The Society orders printing on May 19th. Halley takes charge of publication. He corresponds with Newton through the summer. On June 30th, Samuel Pepys licenses the book. Book 2 is sent to Halley on March 1st, 1687. Book 3 on April 4th. Printing completes by summer. The correspondence between Newton and Halley ends on July 5th, 1687. The Principia is published. This timeline is documented in letters held at Cambridge in the Royal Society archives. We know this from a 2020 study that established a new census of first edition owners. Researchers identified 387 surviving copies, much more than the previous estimate of 250. This suggests wider initial readership and greater early impact than previously thought. The book was not obscure or ignored. It circulated among mathematicians, astronomers, natural philosophers across Europe. It was read, annotated, studied. Copies show margin notes, readers working through the proofs, trying to follow Newton's geometric demonstrations. The book is difficult, written in Latin, dense mathematics, but those who master it recognize its significance immediately. The famous Monsieur Newton has brushed aside all difficulties together with the Cartesian vortices. He has shown that planets are retained in their orbits by gravitation toward the sun, and that elliptical orbits necessarily follow. Huygens is one of the greatest scientists of the era. His endorsement matters. Even though he disagrees with Newton on some points, he acknowledges the achievement, the mathematical rigor, the explanatory power. French mathematician Alexis Clairaut assesses the Principia in 1747. The famous book of mathematical principles of natural philosophy marked the epoch of a great revolution in physics. The method, followed by its illustrious author, Sir Newton, spread the light of mathematics on a science which up to then had remained in darkness of conjectures and hypotheses. By the mid-18th century, Newtonian mechanics dominates European science. From Huygens on centripetal force, from thinking about orbits since Hooke correspondence, he understands motion is change governed by force. Third, astronomical knowledge. He knows Kepler's laws, planetary positions, orbital periods, can test predictions against phenomena. Fourth, Halley's specific question as focus. What curve does inverse square force produce? This concentrates Newton's attention, but crucial factor is synthesis. Newton sees connections, realizes planetary orbits, falling bodies, projectile trajectories, pendulum oscillations, all follow same principles. Once you state laws of motion clearly, everything else is mathematics. This unification is revolutionary. Before Newton, celestial and terrestrial mechanics are separate. Newton unifies. Same force pulls apple and holds moon. Same laws govern throne, stone, and orbiting planet. One physics, one set of laws. Universal. That there is no difference in kind between celestial and terrestrial phenomena. Newton provides both the mathematics and the physics. He shows that unity is not just philosophical aspiration, it is demonstrated reality. The same inverse square law explains planetary orbits and projectile paths. The same principles of motion apply everywhere. This is the power of mathematical physics. Not just describing nature, explaining it, predicting it, unifying it. Definitions must come first, then laws of motion, then theorems about forces and trajectories, then applications to specific problems. This organization is not just pedagogical convenience, it reflects the logical order of truth. You cannot prove theorems about planetary motion without stating laws of motion. You cannot state laws of motion without defining force and mass. Everything must be built from foundations. Newton's approach becomes the model for theoretical physics. State principles clearly, derive consequences rigorously, test predictions against observation, revise theory when necessary. This method works. It allows physics to progress systematically. Each generation builds on the last. Euler extends Newton's laws to rigid bodies and fluids. Lagrange develops analytical mechanics using energy principles. Laplace applies Newtonian gravity to celestial mechanics. Maxwell uses similar methods for electromagnetism. Einstein follows the same approach for relativity. State axioms, derive consequences, test predictions. This is Newton's legacy, not just the specific laws, but the method itself. He builds a comprehensive system. He shows how his methods apply to diverse phenomena: comets, tides, precession of Earth's axis, motion of moon with perturbations from sun, resistance of fluids to motion of bodies, propagation of waves in air. Each application demonstrates the power of the mathematical approach. Each success builds confidence in the underlying principles. By the time Principia is complete, Newton has created not just a theory, but a research program. Other scientists can apply Newtonian methods to new problems, can extend the theory in new directions, can build on the foundation he established. That mathematical rigor can be combined with physical insight, that a single set of principles can explain diverse phenomena. This recognition drives Newton through the next 2 years of intensive work. He knows he is building something historically significant, something that will transform natural philosophy. The work is exhausting, consuming. Newton's secretary later describes how absorbed Newton was, how he forgot everything except the manuscript. But the result justifies the effort. The Principia becomes one of the most important scientific works ever published. Everything focused on this single problem: motion, force, trajectory, Kepler's laws, the inverse square relation, the shape of orbits. How do all these pieces fit together? What are the underlying principles? What mathematics is needed? How should the argument be structured? These questions circle in Newton's mind. He's been thinking about them for months, for years, since Woolsthorpe during the plague, since correspondence with Hooke, since Halley's visit in August. Derive the inverse square law for elliptical orbits. Solve the inverse problem. Give an inverse square force, find the trajectory. Extend to resisting media, consider applications to projectiles. This is the structure. This is what Newton writes in the next few hours or days. The 9 pages of De Motu, the foundation of Principia, the beginning of modern physics. The manuscript Newton sends to Halley in November 1684 does not contain all of classical mechanics. The laws are not yet fully stated, the applications are not yet complete. Universal gravitation is not yet formulated. But the framework is there, the method is established, the key results are proved. From this foundation, everything else follows. Over the next 2 years, Newton fills in the gaps. He states the laws explicitly. He proves intermediate results. He applies the theory to the solar system. He tests predictions against observation. He writes 500 pages instead of 9, but the breakthrough happens before any of this. The breakthrough is seeing that a systematic mathematical theory of motion is possible, that scattered insights can become rigorous science, that the universe operates by discoverable laws. The Principia title page says July 5th, 1686 for the imprimatur. Samuel Pepys, as president of the Royal Society, signed the authorization. But the book was not printed until summer 1687. So July 5th, 1687 is the publication date. De Motu was sent to Halley in November 1684 and registered with the Royal Society on December 10th, 1684. This is documented in Royal Society records. Halley's visit to Newton was August 1684. Multiple sources confirm this. The timing of everything else is less certain. When exactly in November did Newton finish De Motu? How many days or weeks did the actual writing take? How much was written continuously versus spread over time? These details are lost. Newton did not keep a journal. His secretary's reminiscences are from decades later. What we know is the result: 9 pages of geometric proofs that change the history of science. This suggests intense focus on the Principia project during this entire period. He was not just writing, he was thinking, calculating, working out mathematical details, testing different approaches. The absence of chemical notes indicates that Newton set aside all his other pursuits. Alchemy was a serious interest for him, years of regular experiments, careful records. But it all stops in May 1684, just before Halley's visit in August. This is not coincidence. Something about the orbital dynamics problem captured Newton completely. He abandoned everything else. Or did Newton work all this out independently and simply refuse to credit Hooke? The documentary evidence is mixed. Newton clearly knew about orbital mechanics before Hooke's letter. His work from 1666 shows calculations on centripetal force. But the 1679 correspondence may have prompted Newton to think about elliptical orbits specifically, to move beyond circular motion, to tackle the general problem. Newton later minimized Hooke's contribution. In letters to Halley, Newton argues that Hooke only guessed at results Newton proved rigorously. This is true, but perhaps unfair. Hooke's physical intuition was valuable, even if he lacked mathematical skill. The question of priority and credit matters less than the scientific achievement. Newton synthesized many sources into a unified theory. Galileo, Descartes, Huygens, Hooke, Kepler. All contributed pieces. Newton assembled the picture. Thermodynamics. Each field develops by discovering mathematical laws, by building theories from fundamental principles. Newton did not invent experimental science. Galileo and others came before. But Newton showed how to combine mathematics and experiment into rigorous theoretical science. This becomes the model, the standard, the goal every science tries to achieve. Before Newton, philosophers debated whether nature operates by necessity or purpose, whether motion requires continuous causes or just initial impulses, whether heavenly and earthly realms differ fundamentally. Newton settles these questions by demonstrating what is actually true. Nature operates by mathematical laws. Motion continues by inertia unless forces act. The same principles apply everywhere. These are not philosophical preferences. They are demonstrated facts. The success of Newtonian mechanics proves its assumptions correct, at least for the domain of objects larger than atoms and slower than light. Philosophy must accommodate what physics discovers. This shift from armchair speculation to evidence-based reasoning characterizes the Enlightenment. Newton's Principia is central to that transformation. Voltaire popularizes Newtonian science in France. Pierre-Simon Laplace extends celestial mechanics to include perturbations and long-term stability of the solar system. Joseph Louis Lagrange reformulates Newton's laws using analytical methods. Leonhard Euler applies Newtonian principles to fluids and rigid bodies. Every major scientist builds on Newton's foundation. By the end of the century, Newtonian mechanics is universally accepted in Europe. Not immediately after publication in 1687. Initial reception was mixed. Continental philosophers preferred Descartes' vortex theory, but over decades, the success of Newtonian predictions convinced skeptics. Halley's comet returned in 1758 as Newton's theory predicted. Clairaut calculated the return date accurately using perturbations from Jupiter and Saturn. This validated the theory publicly and dramatically. The breakthrough in late 1684 sets all of this in motion. Without De Motu, there is no Principia. Without Principia, there is no Newtonian revolution in science. The 9 pages Newton writes in November 1684 contain the seeds of modern physics. Not the complete theory, but the essential framework, the method, the key results. Everything else grows from this. Newton expands it over 2 years into 500 pages. Later, scientists apply it to new phenomena. Generations of students learn the laws. The impact cascades through centuries, all beginning with those hours in Cambridge when Newton finally sees how to organize his scattered insights into a coherent system. We have his later descriptions of keeping problems constantly before his mind until solutions emerge slowly. We have testimony from his secretary about Newton's absorption in work, but the internal process remains mysterious. How does synthesis occur? How do scattered pieces suddenly cohere? Why, after 18 years of intermittent work, does clarity finally come in late 1684? Perhaps Halley's visit provides the catalyst. Perhaps 3 months of focused thought reaches critical mass. Perhaps Newton simply needed time to work through the mathematics. All these factors contribute, but the precise mechanism of insight eludes analysis. Registered with the Royal Society, December 10th, 1684. This tract contains the first rigorous mathematical derivation of planetary motion from force laws. It proves that inverse square forces produce conic sections, that any central force produces equal areas in equal times, that Kepler's laws follow from deeper principles. It introduces the term centripetal force. It applies geometric calculus to physical problems. It lays foundation for classical mechanics, not bad for 9 pages. Abandoning alchemy and theology, writing and revising, testing calculations, building the logical structure, only then does the manuscript take shape. Only then does Newton see clearly enough to write coherently. The breakthrough is not sudden inspiration. It is patient synthesis of long accumulated material. There is no soil core, but there is something almost as revealing: the manuscript itself. Add 3965 at Cambridge University Library. Folios 55 to 62, Newton's handwritten draft, crossouts and corrections, diagrams of ellipses and force vectors, geometric constructions with Latin labels. This is not clean copy, this is working draft. Newton thinking on paper, trying one approach, revising, trying another. Getting it right. The manuscript shows that even in those breakthrough hours or days, the work was not effortless. Newton struggled with wording, with organization, with geometric proofs, but he pushed through. He completed the tract. He sent it to Halley, and in doing so, he changed the world. Not lucky accident. Methodical work over years, culminating in focused synthesis over months. The universe operates by mathematical laws discoverable through reason. Newton proved it. The breakthrough came when scattered truths assembled into system, when definitions clarified, when laws emerged, when theorems followed. Late 1684. A quiet room at Trinity College, papers everywhere, one man writing, and physics began.